You know, when you're running like a massively complex program on your computer, maybe you're rendering a high-definition video or something.
Oh, yeah, or compiling a massive database.
Right, and suddenly the screen just completely freezes, the cooling fans kick on, and they start spinning like jet engines.
Yeah, the laptop case is practically radiating heat at that point.
Exactly. But the progress bar on your screen is just totally stuck at 99%. To anyone just looking at the monitor, I mean, it seems completely broken.
But under the hood, though, billions of calculations are firing off every single second.
Right.
The system is actually working harder than it has at any other point in the process.
Yeah.
It's just entirely invisible to you at that exact moment.
Yeah.
Because, well, all the effort is going into internal processing.
Yeah, instead of updating the user interface.
Exactly.
And honestly, that is the perfect metaphor for what it feels like living right now in the year 2026. So welcome to today's deep dive.
Glad to be here.
We put this together specifically for you, the listener, because if you're paying any attention at all, you're probably trying to make sense of this wild technological moment we're in.
It's definitely a confusing time for a lot of people.
It really is. I mean, we are constantly surrounded by the hype of AI advancements, autonomous vehicles, rapidly scaling tech, all of it.
Right, but then you look around your neighborhood or look at your paycheck or even national GDP reports.
Yeah, and you're wondering if we're in the middle of this unprecedented technological revolution, why does it feel like our economic statistics and our daily physical realities are just lagging so far behind the promise?
Well, it's really the defining question of our time. Because the future of technology isn't actually being held back by a lack of ideas.
Or lack of software innovation, right?
Right. It's being bottlenecked by invisible economic restructuring, massive energy bills, and just the sheer physical limits of computation.
So our mission today is to cut through all that noise and explain the actual mechanics of what is happening behind that frozen progress bar.
And to do that, we're leaning on 4 specific pieces of research.
Yeah, we've got some great sources. We're pulling insights from an NBER economic working paper on the modern productivity paradox.
We're also looking at Rich Sutton's legendary essay, The Bitter Lesson.
Plus, a major study from the journal Joule on the energy footprint of AI. And finally, Rodney Brooks's January 2026 predictions scorecard.
Which really tracks where the rubber actually meets the road.
Exactly. So to really understand this moment, we have to start by looking at the macro-level economic mystery.
Right, so the National Bureau of Economic Research, or NDER, they published a paper that points out this glaring contradiction in our modern economy.
And what's the contradiction?
Well, we have AI systems right now that can match board-certified dermatologists in diagnosing skin cancer.
Wow.
Yeah, and we have algorithms that have optimized massive data center cooling grids, reducing their energy use by like 40%.
Yeah, I mean, those sound like massive economy-altering breakthroughs.
They absolutely do. Yet, if you look at the data from 2005 to 2016, U.S. labor productivity growth averaged a pretty dismal 1.3% per year.
Wait, really?
Yeah.
Just 1.3%?
Yeah, that is actually less than half the rate of the decade prior.
Yeah.
So the fundamental question the researchers ask is, if AI is so transformative, why isn't it showing up in the productivity statistics?
Why aren't we all suddenly twice as productive?
Exactly.
But wait, are you telling me that all the billions of dollars tech giants spent over a decade resulted in stagnant or even negative productivity? How did investors not just completely panic?
Oh, many of them did panic. And the researchers actually outlined 4 potential theories for this gap.
Okay, let's hear them.
The first is simply false hopes. Basically, the cynical idea that the tech is just overhyped.
Like it's a shiny toy that won't ever deliver real economic value.
Right. The second theory is mismeasurement, meaning our traditional GDP metrics just don't know how to track free digital goods.
Oh, I get that. Like if an AI writes an email for you for free, GDP doesn't go up, even if your life genuinely gets easier.
Precisely. Then the third theory is rent dissipation.
Rent dissipation.
Yeah, it's the idea that the economic gains are real, but they're entirely hoarded by a few massive monopolies.
Ah, so the broader economy just doesn't feel the impact.
Exactly.
Well, I can see the argument for all of those, especially the monopoly hoarding one. But the researchers land on a fourth theory, right?
They argue the most likely culprit is implementation and restructuring lags.
Okay, unpack that for us.
So to understand this, you have to realize that AI is not just a new software application. The NBER paper defines AI as general purpose technology, or a GPT.
Meaning it's a foundational shift, like on the exact same level as the invention of the steam engine or electricity.
Right. And when you look at the history of general-purpose technologies, they never deliver productivity gains immediately.
Yeah, like when factories in the early 1900s switched from steam power to electricity, they didn't just unplug a steam engine and plug in an electric motor.
Exactly, because the entire layout of a steam factory was based around one massive central drive shaft.
Right, so to use electricity effectively, they literally had to tear down the factory, give every workstation its own small motor, and entirely redesign the assembly line.
And that physical and organizational redesign takes decades. The modern equivalent of that factory redesign is what the NBER paper calls the J-curve of mismeasurement.
The J-curve.
Yeah. To implement a fundamentally new technology, companies have to invest in massive amounts of what economists call intangible capital.
So spending millions, retraining workers, redesigning business processes, that kind of thing.
Exactly, developing entirely new software pipelines from scratch.
I was actually thinking about how to visualize this J-curve for you, the listener, and it's exactly like signing up for a gym and hiring an expensive personal trainer.
That's a great way to look at it.
Right, because for the first few months, your bank account drops because you're paying the trainer. Your free time is totally eaten up by the workout.
And physically, your muscles are just incredibly sore and you actually feel weaker.
Exactly. If a scientist measured your productivity during those first 2 months, it would actually be negative. You're spending resources and you're just hurting.
But the physical gains, the actual output of all that work, they only show up much, much later.
Yeah, after the foundational restructuring of your muscles is already done.
That analogy perfectly captures the mechanics of the J-curve. Economically, we are just in the sore muscle phase right now.
We're sweating it out.
We really are. We're measuring the massive inputs, the billions of dollars spent building AI systems and restructuring corporate workflows.
But the outputs haven't been realized yet because the new factory floors are still being built.
Right. The key takeaway for you, listening to this, is that historical stagnation in productivity data does not justify forward-looking pessimism.
The progress bar looks frozen, but the calculations are firing. Yeah. So if the broader economy is sweating it out in this invisible gym phase, building the infrastructure, I want to look at the AI systems themselves.
Let's do it.
Because how did the software suddenly get so good that it warranted this massive economic restructuring in the first place? After decades of relatively slow, clunky progress, what actually changed?
Well, to answer that, we have to look at the philosophy of how we build these systems. Rich Sutton, a highly influential computer scientist, wrote an essay called The Bitter Lesson.
The bitter lesson. Sounds intense.
It is, kind of. It breaks down the last 70 years of AI research. For decades, the smartest people on Earth tried to build their own human knowledge and logic directly into machines.
They thought the way to create intelligence was to literally decode human thought and program it line by line.
Yeah, exactly.
Give me an example of what that actually looks like in practice.
Well, take computer vision. Researchers used to spend years writing code that explicitly told a computer how to look for a physical edge, or a shadow, or a cylinder.
Oh, wow.
Or take speech recognition. Linguists tried to teach computers the complex grammatical rules of language, the physical structure of the human vocal tract, and the rules of phonemes.
Phonemes, like the actual sounds we make.
Right. They built massive, highly curated linguistic rulebooks.
I have to play devil's advocate here for a second.
Go for it.
Isn't it fundamentally strange and maybe a bit insulting to our egos that to build artificial intelligence, we ultimately had to stop trying to make it think like an actual human?
Oh, it's a huge blow to the human ego.
It just feels totally counterintuitive that an arbitrary neural network crunching endless data works better than a beautifully designed set of human rules.
It is an absolute blow, which is exactly why Sutton calls it bitter. Researchers devoted their entire careers to encoding human logic, and those human-centric approaches always hit a wall.
They just stopped improving.
Yeah. The breakthrough, the bitter lesson itself, is that trying to codify human intuition always loses in the long run.
So what wins?
The only approach that truly works is abandoning human logic entirely and using general methods that leverage massive computation, specifically the methods of search and learning.
And this relies heavily on Moore's law, right? The historical trend where the number of transistors on a microchip doubles roughly every 2 years.
Precisely, making computing power exponentially cheaper and faster. Sutton points out that human-coded AI looks great in the short term when computing power is limited.
Because you're being efficient with the logic.
Right. But as Moore's law marches on and compute becomes incredibly cheap and abundant, Brute force algorithms utterly destroy the elegant, human-coded ones.
The historical examples of this are just fascinating to me. Take Deep Blue beating the world chess champion Garry Kasparov back in
A
1997.
huge moment.
The chess purists were horrified because Deep Blue didn't think about chess the way a grandmaster does, using intuition, positional understanding, or strategy.
It didn't have human logic at all.
No, it just used massive, deep search, brute forcing millions of possible future board states faster than Kasparov could process them.
And the exact same thing happened with speech recognition. It only started working well when researchers threw out those linguistic rule books we mentioned earlier.
And what did they replace them with?
They switched to statistical models, like hidden Markov models, and later deep learning.
Let's pause on that for a second. What actually is a hidden Markov model, and why did it beat the linguists?
Well, instead of trying to teach a computer the rule that I goes before E, except after C, a hidden Markov model just chops an audio signal into tiny statistical frames.
So it doesn't know grammar at all.
It doesn't know what a noun or a verb is. It just uses massive amounts of data to calculate the mathematical probability that one specific sound follows another.
It's just pure statistics driven by raw computing power.
Exactly. The profound realization about ourselves here is that the actual contents of our minds, how we intuitively recognize a face or understand a sentence, are simply too irredeemably complex to write down in code.
We just can't map it out.
No, we shouldn't try to build into the machine what we've discovered. Instead, we need to build empty statistical metamethods that can discover things on their own.
Fueled by raw, unfiltered computing power.
Right.
But, I mean, Sutton's whole philosophy ignores one massive glowing red warning light. You can't just scale computation infinitely without consequences.
No, you definitely cannot.
Computation isn't just invisible math floating in the digital ether. It requires physical hardware. It requires burning actual coal and natural gas to power the data centers.
And this is exactly where the theoretical potential of AI crashes headfirst into physical reality.
Right, because we are transitioning from the realm of software into the realm of thermodynamics.
Exactly. Alex DeVries published a major study in the journal Joule examining the massive energy footprint of AI.
And the scale is just mind-blowing.
It is. To understand it, you have to separate AI's energy usage into two distinct phases: the training phase and the inference phase.
Break those down for us.
Sure. So the training phase is when you were building the model. You're feeding it terabytes of data, letting it run its statistical learning processes.
It's like sending a student to the library for 4 years to read every book ever written.
That's a perfect analogy. Training the GPT-3 model, for instance, took about 12,287 megawatt hours of electricity.
Which is a staggering amount of power. But, I mean, it's a one-time sunk cost. Once the model is trained, it's done.
Right, but that's actually the huge misconception. The real energy hog is the inference phase.
Inference, okay.
Inference is what happens when the model is actually live out in the world, generating responses for 100 million users.
So it's the student actively answering questions on a test, millions of times a second.
Exactly. DeVries' data shows that in early 2023, just keeping ChatGPT running and generating text required roughly 564 megawatt hours every single day.
Every single day.
Every single day.
Let me put that in perspective for you. A standard Google search, the kind we've been doing for 2 decades, uses about 0.3 watt-hours of electricity. But an AI-powered interaction uses anywhere from 3 to 9 watt-hours. That means every time you ask an AI a question, you are using up to 30 times more physical energy than a traditional search.
Which is wild.
Yeah.
And it forces us to look at the worst-case scenario.
What's the worst case?
Well, DeVries calculates what would happen if every single standard Google search was replaced by an AI interaction.
Okay.
To physically process that much inference, the industry would require over 4 million specialized NVIDIA graphics processing units, or GPUs.
Oh.
And the electricity consumption for that single application would skyrocket to up to 29.3 terawatt hours a year.
29.3 terawatt hours. That is roughly the same amount of electricity consumed by the entire country of Ireland, just for search.
Just for search.
If inference is that expensive and requires the power grid of a European nation, just one feature, isn't the AI bubble just going to pop when the power companies simply say, no, we don't have the capacity?
The power grid is definitely a major issue, but the global supply chain is actually hitting the brakes first. Yeah, you can't just will 4 million advanced GPUs into existence. NVIDIA physically cannot build them fast enough.
Why not, though? I mean, they're the most valuable company in the world. Why can't they just build more factories?
Because the bottleneck goes all the way down the supply chain to TSMC.
The primary semiconductor manufacturer in Taiwan.
Right. These AI chips require a highly specific advanced packaging process called CoWoS chip on wafer on substrate.
Right, which stacks the memory directly next to the processor to speed up those massive calculations.
Exactly. And TSMC simply doesn't have the physical factories to do this packaging at that scale.
Yeah.
They've publicly stated those plants won't hit the necessary volume production until 2027.
So even if you have the money, you can't get the chips.
Nope. And furthermore, the economics of DeVries' scenario are just brutal. Buying those 4 million servers would cost Google around $100 billion.
Good grief.
That capital expenditure would essentially wipe out their operating margins.
But the demand for AI is so high that people are getting desperate, right? And creative. The paper mentions this phenomenon called mining 2.0.
Oh yeah, mining 2.0. Former Ethereum crypto miners, whose rigs became obsolete, are now repurposing their old, heavily used, less efficient GPUs.
To run AI inference tasks for smaller companies.
Exactly. And DeVries warns that this desperation is going to trigger Jevons paradox.
Jevons paradox. I love explaining this one because it literally happens everywhere.
It's a classic economic principle. Intuitively, you'd think that making a technology more energy efficient would decrease total energy consumption.
But Jevons paradox proves the opposite, right? Increasing the efficiency of a resource actually leads to a massive increase in its total consumption.
Exactly.
It's like a city realizing they have terrible commuter traffic, so they spend billions building a massive, highly efficient 10-lane highway to reduce congestion.
Right, to fix the problem.
But instead of fixing the traffic, the new efficient highway just encourages way more people to move to the suburbs and start driving.
And then what happens?
Within a year, the 10-lane highway is in total gridlock. The exact same thing applies to AI. If engineers figure out how to make AI models more computationally efficient, it might not save power.
No, it will just make AI cheap enough to put into every single toaster, refrigerator, and app.
Creating an absolute explosion in demand that eats up even more of the energy grid.
Exactly. So we have the economic lag of the J-curve, Sutton's mandate to rely on massive computation, and DeVries' warning about the hard physical limits of hardware and energy grids.
It's a lot colliding all at once.
It is. So if we mix all these ingredients together, where does that leave us right now in the present day of 2026?
Well, to answer that, we turn to Rodney Brooks. He is an absolute legend in the robotics and AI field.
Yeah, he's been working in it for 50 years, helped found iRobot, and knows exactly how hard it is to put smart software into a physical machine.
And every year, he publishes a predictions scorecard, holding his own past predictions accountable. He tracks the brutal difference between software hype and actual large-scale physical deployment.
Right. And Brooks draws a very sharp contrast between technologies that manage to scale successfully in the physical world and those that hit a wall.
Give us an example of one that worked.
Well, he points to a physical deployment that did scale miraculously, SpaceX's Falcon 9 rocket.
Oh, yeah.
By the start of 2026, it had hit 582 launches with a sustained 38% year-over-year growth rate for 8 years.
That's incredible.
Brooks compares that deployment volume to the WWII V2 rocket. It is an astonishing physical and logistical achievement.
But then you contrast that literal rocket science with self-driving cars. Brooks notes that Cruise, General Motors' self-driving arm, failed completely and disbanded after dragging a pedestrian.
Yeah, that was a disaster. That left only Waymo and Zoox still standing in the U.S.
And there's a specific anecdote from his scorecard that I think defines this entire deep dive.
Right.
December 20th, 2025.
Right, the blackout.
There was a massive power outage in San Francisco. Traffic lights went dark across the entire city.
Think about what a human driver does when a traffic light goes dark.
You rely on unwritten social protocols. You treat it as a four-way stop.
Right. You inch forward, you make eye contact with the other drivers, you wave people through. You use human intuition to navigate the chaos.
But the Waymo autonomous cars encountering these dark signals, they didn't have that intuition.
No, they didn't. They were programmed to prioritize safety, which meant requesting a human-level confirmation from a remote center before proceeding through a dead intersection.
And because hundreds of intersections went dark simultaneously, it created a massive backlog of requests to the remote human operators.
The cars couldn't get permission to move, so they just stopped.
They paralyzed the intersections, causing total gridlock in San Francisco.
It perfectly illustrates the fragility of the AI inference phase when it meets the real world. I mean, why does a rocket scale but a car fails?
Well, a rocket operates in the vacuum of space. It is mathematically highly complex, but the environment is ultimately empty and predictable.
Exactly. A car operates in the infinitely messy, chaotic, unpredictable environment of human society.
It is the exact irredeemable complexity that Sutton warned us about, but applied to physical safety.
Yes. And Brooks's other predictions for the next decade double down on this friction between software and physical reality.
Like what?
Well, he predicts that humanoid robot dexterity will remain pathetic compared to human hands for the next decade.
Pathetic. Why?
The reason for that is mechanical, not software-based. Human hands have millions of nerve endings and incredibly complex biological tendons.
Right, whereas actuators and electric motors haven't experienced Moore's law.
Exactly. A robotic hand is still just clunky metal and gears. You can't just code a better gear.
Wow.
Brooks also notes that digital quantum computers will continue to struggle.
Let's clarify that for the listener. What is the actual problem with digital quantum computing?
Digital quantum bits, or qubits, are highly unstable. They flip randomly due to the slightest temperature change or even microscopic noise.
So they make a lot of math errors.
Right. To fix one error, you need hundreds of backup qubits just to correct the math, which scales the hardware requirements impossibly fast.
So what's the alternative?
Brooks predicts that analog quantum computers, which don't try to force digital logic, but instead use raw physical systems to emulate other physical molecules, will be the ones to actually find success in materials science.
And crucially, Brooks predicts that large language models, the text generators we use every day, will have to be strictly boxed in.
Yes, because of hallucinations.
Right.
Since these models use statistical methods like hidden Markov models, they don't actually know what a fact is.
They just know what words mathematically look good together.
Exactly. So in high-stakes real-world applications, Brooks says they will need rigid, non-AI mechanisms wrapped around them to explain exactly where their data came from.
Otherwise, they are just too dangerous or unreliable to use in medical or legal deployments.
Absolutely.
Well, we've covered incredible ground today. Let's summarize the landscape for you. We've seen through the NBER economic paper that we are currently living in the J-curve of the productivity paradox. The progress bar looks frozen because we're doing the heavy, invisible, expensive lifting of fundamentally restructuring our corporate environments.
And we know from Rich Sutton's bitter lesson that scaling massive computation and abandoning human logic is the only proven way forward to make AI smarter.
But thanks to Alex DeVries's energy data, we know that this brute force path is severely bottlenecked by the thermodynamic realities of our energy grids and the fragile semiconductor supply chain.
Right.
And as Ronnie Brooks showed us with the San Francisco blackout, throwing massive compute at a problem still doesn't solve the chaotic physical edge cases of the real world.
It really doesn't.
Yeah.
And I want to leave you with a final thought to mull over, and it builds directly on the clash between Rich Sutton and Alex DeVries.
Okay, let's hear it.
Consider this. Sutton's bitter lesson asserts that the only path to true artificial intelligence is leveraging endlessly scaling computation. But DeVries' data proves that computation physically cannot scale endlessly. We are already hitting the hard thermodynamic limits of the global energy grid and the manufacturing limits of silicon.
Wow.
So for perhaps the first time in 70 years, the bitter lesson is on a direct collision course with the laws of physics.
That's incredible to think about.
If we can't build our way out of the problem with raw power anymore, will we finally be forced to abandon the bitter lesson and figure out how to make AI actually think smarter rather than just work harder?
That is a brilliant tension to end on. Because, I mean, if the fans on your computer are spinning as fast as they physically can and the system is overheating, you can't just keep plugging it into bigger power outlets.
No, you can't.
Eventually, you have to open up the machine and fundamentally rewrite the code to be more elegant. Thank you so much for joining us on this deep dive. Keep questioning the invisible limits of the world around you, and we'll catch you next time.